Welcome to our webinar, Best Way to Transform Light Response Curves. The right protocol depends on the information you're looking for. This is presented by Dr. Jim Bunce. Jim built his first photosynthesis system as a graduate student 48 years ago, and he's been performing leaf gas exchange measurements ever since. He has 40 years of research experience with the USDA Agricultural Research Service in Beltsville, Maryland, as an environmental plant physiologist. His focus has been on photosynthesis, stomatal conductance, and plant-water relations and their response and acclimation. Most recently, adaptation to the global change factors of rising carbon dioxide concentration and temperature. We're going to have Jim present his webinar. We ask that you hold your questions until the end so that we can allow him to do his presentation, and then we will address every question we can that is put into the chat, and if we can't, we'll email you directly. So Jim, would you like to do your presentation?
Okay. So welcome to PP Systems webinar. And Carrie gave my title, which is Best Way to Perform Light Response Curves. What information are you looking for? Let's start by looking at what information we can get from light response curves. So here is just a plot of CO2 assimilation rate, A, on the y-axis, and photosynthetic photon flux density on the x-axis. And the green symbols indicate data points plotting A versus PPFD. So some of the parameters that we can obtain from a curve like this for any species are the maximum rate of assimilation rate at about 2,000 micromoles of light, and that's about full sunlight. So we seldom go above that. You can estimate the PPFD required to give you something like 90% of the saturated rate, or whatever percentage you're interested in. You can look at the initial slope of the response curve and define an initial slope from the data. You can determine the light compensation point, which is the PPFD value at which assimilation rate equals 0. And you can estimate or measure a respiration rate, which is the CO2 assimilation rate when PPFD is 0. So those are 5 basic parameters that one can obtain from a single leaf response. The alternative way of looking at this is to fit some model parameters, and they're 2 basic ones. One has been around for a long time. It's called a traditional non-rectangular hyperbola. And I gave you a fairly recent reference to that, which I'll present at the end. It's not particularly mechanistic, but the kinds of information you can get out of it are the initial slope, the maximum rate of assimilation, a shape parameter, and respiration rate. And a newer model, which claims to be more mechanistic, and it's by Yi and several co-authors, and I'll give you that reference at the end also. And similarly, it also defines an initial slope, what they call a J max, which combines a shape parameter and a maximum CO2 assimilation rate and a respiration. So you can either pick off parameters yourself, or you can fit your data curve to a model and get parameters that way. There is one special case when you're interested primarily in rates at very low PPFDs, and particularly useful for respiration or CO2 compensation point. And it's kind of a special case where you don't really care about what the plant does at high light, but you're looking in detail at what it's doing at low light. And to do those kind of measurements, you need need to collect data in a different way. You need to try and maximize the area of the leaf area that's exposed by using a large cuvette window, and to run the instrument at low flow rate to maximize the CO2 differential for each of these points. So if you, in fairly dim light, we're only going up, less than 150 micromoles per meter squared per second for the photosynthetic photon flux density, and we're looking at a simulation rate again. And some of the parameters you can get from this is the light compensation point, which you mentioned before, which is the PPFD at which the rate is 0. You measure at 0 light, you measure a CO2 exchange rate, which is called dark respiration, and that's a measured value. But you can also take data points and extrapolate them backwards to the y-axis and get that intercept, which is called light respiration. So that's an extrapolated value. And it's an estimate of what mitochondrial respiration is in the light. And that's smaller than what mitochondrial respiration is in the darkness, because light provides some of the energy so that some of the dark respiration is not needed, and so the plant doesn't do it. So this is kind of a special case where you're interested in these kind of parameters, and there, as I said, you need to maximize the leaf area exposed and to minimize the flow rate in order to get more accuracy at these low fluxes. But if you're trying to do a full curve, the first question obviously is, what direction do we want to change light? Do we want to start at low PPFD and go up, or start at high PPFD and come down? And the answer almost always is we want to start at high PPFD and come down. And the reason is because this equilibration after an increase in PPFD is very slow. And this is just an example of that, where we've given a leaf which is operating here at a rate of around 10, and it's going to go up 30%. We've given it a step increase in light that eventually is going to bring the rate up by about 30%. But you can see just plotted time points that it takes in excess of 30 minutes for it to accomplish this 30% increase in CO2 assimilation rate. So if you're trying to do a whole light curve this direction, it's going to take forever. So, and the question is why? And the answer primarily is slow changes in stomatal conductance. And this is a plot now of stomatal conductance against time. And you can see, and it's still only doing roughly a 30% change, but you can still see that it takes it's just a very, very slow, gradual response. And it takes more than 30 minutes to get there. So while stomatal conductance is slowly changing, you can see actual gyrations going on in the internal CO2 concentration. So we've plotted here for the same data set, the internal CO2 concentration over time. And you can see here it starts at 210 more or less. And initially, when photosynthesis responds more quickly than the stomates do, the CI actually goes down initially. And then as this photosynthesis has geared up as much as it can, and then it's just waiting for the stomates to open, so then CI comes up, and it took probably 40 minutes for the CI to stabilize. So, so going step increases in light is a very slow process. So we tend to start at high light and decrease, but how fast can you decrease light? And that's a good question. We have plotted here, I've tried 2 different species here, and we've done a comparison of 100 seconds per step versus 300 seconds per step down in PPFD. And these are plotted, they're actually both plotted here. It looks like only the blue dots are shown, but they're actually black dots basically directly underneath the blue dots. So the point is that for this species, which is a Lilly, with sort of modest photosynthetic rates, that these 2 rates of change in PPFD stepping down give virtually indistinguishable rates of CO2 assimilation at each step. So it doesn't really matter. We can go as slow as 300 seconds per step or faster at 100. And does this happen for a species that has a higher maximum rate? And this is happens to be quinoa. And again, both plots, both rates are plotted here. And it only looks like the one data set, but that's because the black and blue dots basically are superimposed at each step in light. So for this species also, there's no distinguishable difference in the results you get when you do 100 seconds per step or 300 seconds per step. So that's assimilation rate. How about stomatal conductance? And here we see considerable difference between the rate of change in step down of PPFD. If you do it quickly, which is the blue dots here, in Lilly, basically you're not getting any change in stomatal conductance over the whole PPFD curve. It's basically flat. If you give it time, 300 seconds per step, then you do see a gradual decrease in stomatal conductance as you decrease in PPFD. When we look at quinoa, which is a more active species, again, in this species, even with the rapid changes in step, you get some decrease in stomatal conductance at the lower end of PPFD. It's not very much, but it is here in this species. But it's very small change compared to what you get when you do a slow equilibration, and you get from 300 to 1300, which is a big change in stomatal conductance over that curve. So the rate of change does make a difference if you're interested in stomatal conductance. So what happens to CI? Because in Lilly, where we were slow, there was no change in stomatal conductance versus a significant change in stomatal conductance as you decrease if you wait long enough and do a slow response. So you can see that here in the CIs. The top end highlight, they're virtually the same. And both of them increase CI as you go down to lower photosynthetic photon flux density, but the two curves separate. So there's a difference in CI at any PPFD down here at the bottom end, depending on whether you're going at 100 or 300 seconds per step. And the same is true in quinoa. Again, at the high end, they're virtually indistinguishable, but at the bottom end, in both cases, CI is going up substantially, and it's different between the two rates of change. So why do these differences in CI between the rapid and slow curves not seem to affect the values of assimilation rate at each step? And this is just a reminder that both for Lilly and quinoa, that the rapid versus slow A versus PPFD curves were indistinguishable for both rates of step downs in PPFD. So how come assimilation rate is not affected if we are getting differences in CI, especially at the low end of the PPFD? We know from Ehleringer and Bjorkman back in '77, the quantum yield is highly sensitive to CI at low CI. So if we're down here in the CI range of below 400, so 300 to 400, you can see this is a fairly steep curve of increasing quantum yield as you go up in CI. So that's kind of a dilemma. And the answer is the differences in CI at low PPFD between the rapid and the slow curves in our two cases were at most about 30 parts per million for both the Lilly and the quinoa. And that difference in CI would result in differences in assimilation rate of only about 0.2 micromoles per meter squared per second, which is just about the limit of resolution of CO2 assimilation rate values. So basically they're invisible because that difference in CI of only 30 parts per million doesn't affect the assimilation rate enough that it's obvious on those kind of curves. However, if you were really interested in quantum yields, then these changes in CI with PPFD at low PPFD would mean your apparent quantum yields would definitely be suspect unless you adjusted the CI values by manipulating CO2 concentration as you were doing light curves. So the conclusions from all of this is that for photosynthetic responses to PPFD, 2-minute steps of decreasing PPFD are adequately long. For stomatal conductance responses, longer steps are needed. For these species, 5 minutes was adequate for those two species. For respiration measurements or light compensation measurements, it's better not to do the complete curve, but to measure directly down at the low PPFDs and use a lower flow rate and a higher area. For quantum yield measurements, you are going to need to manipulate CO2 if you're really going to want to know what quantum yield is at a given CO2 concentration, CI concentration. And these are the 3 references in case anybody needs them. They'll be up on this, will be recorded and be up on the website for anybody who needs those. And that's all I have.
Thank you for the webinar. I was on mute.
Okay.
The references that Jim refers to in his presentation will also be listed in the email that I send you with the link after we're done with the recording. We do have some questions. Assuming you do want to know the compensation points, how would you recommend maintaining a set CI?
There is no automatic way to control CI with any photosynthesis system that I know of. It has, because CI is a measured, it's a calculated parameter. It's not directly measured. So it would be a matter of just trial and error of manipulating CA, either the reference or the sample CO2 concentration by programming in different values and then seeing what your CI is. So that just has to be done by, you can make pretty good guesses about it, but there's no direct way to control CI with the instrument. You have to manipulate CA and see what the CI results from that.
Okay. Okay. If we are interested primarily in Pmax, are fast light curves adequate?
Yes, they're adequate, but for Pmax, if that's what you're interested in, you should just measure that and forget the rest of the light curve. Just do measurements at high light.
Okay. How are you normalizing photosynthetic response rates to plant tissue, leaf area, fresh weight, and thickness?
That's up to you. These are all area-based. And anything beyond that is on the user to, leaf area is the standard. And it's the only logical way to do it, but you can sometimes explain like species differences or growth condition differences in rates per area based on things like mass or protein or chlorophyll or something like that. But that's on the user to do that.
Okay. Is photoinhibition a concern at very high light?
It is for a limited set of species that are adapted to very dim light and basically never get exposed to high light. Then if you're dealing with those species, then you need to take care that you don't start them at light higher than they can tolerate. But that's a matter of trial and error and to know your species. But okay. for most species, that's not a problem.
Okay. In measuring dark respiration of leaves, how long do you practice in measuring dark respiration of leaves, how long to practice dark adaptations of leaves?
That's a interesting question. I don't think anybody has a real firm answer to that. Some people think you need to wait for like half an hour after you turn the lights out before you get a really stable dark respiration rate. I tend to think that I think you need to wait at least a few minutes after the light goes out. But in my experience, dark respiration changes all night long. So there's no point in waiting too long for it because it's never gonna be constant. So what you're looking for is a dark respiration rate that's sort of representative of what it was doing when the light was on. So I wouldn't wait more than a few minutes for it to do what it's going to do.
Okay. What light spectrum are you using for these graphs?
These were all done with, I don't remember the percentages, but it's using the red, blue, green proportions that PP Systems recommends in their manual as being the closest simulation to sunlight.
Okay. Would your step timing change with different spectrum?
I don't have any experience to answer that. I doubt it, but I don't really know.
Okay. So someone says we have LED lights in the growth chamber. How can I find the best of light configuration for Cyrus 3?
The thing to do would be to ask PP Systems to give you the spectrum of their red, blue, and green and white, and then get the spectrum from the manufacturer of your lights in your chamber. And as far as I know, you have to do that comparison and figure it out the best you can from that.
Okay. Well, that was all of our questions. And I think that's about it. So thank you so much, Jim, for your time and for everybody who's attended. This will go out in a couple of days. It'll be a link within an email to everyone. And thank you again. It was great, Jim. And I look forward to the next one.
Okay.
Thank you for attending this webinar. To learn more about how the Cyrus 3 portable photosynthesis system can enhance your research experience, visit ppsystems.com.